say that you are going to do a retry quiz, and so you do your due diligence and you go through and you fix the little couple of questions you missed or whatever, you rework through those, and you're thinking, okay, I'm good there. Oh yeah, I've got to do my practice, right? Like the stuff in the packet. If I were you, if you were like me, and I think a lot of you are, if not all of you are, as I'm doing those practices, I would want to have a good sense that I'm getting them wrong or right. Because it doesn't do you a whole lot of good just to practice if you're just practicing wrong. So I'd wonder, where on earth could there be some solutions to any of those? Do you think I could find something like that? Where would I find it? Right here on Schoology. So check this out. I'm making a video of this, so hopefully folks that aren't here maybe would watch this. So what I'd do is I'd click on the folder for our first semester and look at all of our lovely units. And I would think to myself, right now we're in Unit 3, let's say, right? I was going to do some retry from Unit 3. I would click on the Unit 3 folder and look what shows up at the very start. Some amazing stuff. The Unit 3 packet, not surprising, and then look down below. Concept 6, Practice Solutions. So you click on something like that. And eventually, after some thinking, oh my goodness, look at all those. They're all over the place. They're so nice. And then I could go back and say, I wonder if there's more. Oh, look, there's concept 7, 8, and 9. Right, they're all right there. Right, so you could go through. So a lot of you, when I'm bringing this up, because a lot of you, when you want to do a retry, you'll show me your practice solutions, and I'll say, hey, did you check them? And you give me this look like, what? What are you talking about? So there they are. But for those that have seen that, I've got one more thing I want to show you. You might not have looked at this. Look at the very top folder. Circuits. This is awesome review material. So pretty much from here on out for the whole, and there was some of this in the unit too, so I'm thinking about a test coming up later on this month. If you were looking for more practice material, things to do, and this being in an interesting format, these circuits are awesome. So you click on this, and you see 3 of them, motion and derivatives, which we're going to start looking at tomorrow, relating the graphs of f prime, f double prime, tangent line approximations. These are circuits. These are little documents that are extremely useful and lovely. Let me explain briefly how these work. So you click on one of these, like say motion and derivatives, and up comes this document. Bless you. Okay, so look at the directions up there. It says position, velocity, acceleration denoted by those functions respectively, and it says begin in cell 1. So that would be this upper left. Bless you. You can't see the mouse. You see cell 1, right? Okay, so you work on this, and I know you don't necessarily know how to do this yet, but soon you will. So you would work on cell 1, let's say, and if you did, let's see here, you would get negative 20. You'd get negative 10 if you did cell 1 correctly. Here's how you proceed through the circuit. In cell 1, you got an answer of negative 10. No. Yes. Negative 10. Here's how you proceed. Notice how the other boxes in the circuit say answer 8, answer 1, etc., etc. What you're going to look for is answer negative 10. So I look through this. Ooh, there's an answer 10. There's answer negative 10. So that means this box that is now upper left, that would be my second box. And then my second box would be 6. The answer to that one would be negative 2. So what do I look for my third question? Answer negative 2. Yeah, so I didn't. Oh, look, it's right below. There's usually 2 or 3 pages to these. And the way these typically work is that you start off with the easiest ones and you gradually work your way towards more difficult questions. And so you just kind of like snake your way through the circuit, and eventually you'd come all the way to the last one, and hopefully the last one has the answer 9. You see it? Because box 1, the answer is, it says, answer 9. So hopefully when you get to the very, very last box, you get 9, because that would circle you all the way back around to the start of the circuit. So anyway, just kind of a fun format and some really good practice. So when you're thinking about tests coming up in the future, or just some extra practice for some quiz or whatever purposes you might have, these circuits are pretty nice little activity for you. Make sense? Okay. In your packet, Unit 2, Day 4. Unit 2, Day 4. You're only going to do the first two warm-up questions here. Unit 2, Day 4. So I'll get this on screen. Hopefully, there they are. So, Unit 2, Day 3, we're going to come back around to that. I'm just looking at my warm-ups here. I want you guys to do Unit 2, Day 4 for a warm-up. I'm cutting off the last warm-up. So, FYI, like we got kind of like shafted out of like 20, 25 minutes with the whole Friday schedule thing. So I'm having to try to take like 2 days and smash them down into like a day and a quarter. And I'm going to tell you at the end of class some strategy I'm going to have for you for some extra practicings. I want you to warm up with Unit 2, Day 4, and then we'll go back around to that material on L'Hopital's rule that we just barely introduced. And we will cover that here this morning. So please try Unit 2, Day 4, the first two warm-ups. Or unit, what am I talking about? Unit 3. It says 3 up there, I'm talking about 2. I'm sorry. Unit 3, Day Quattro. Unit 3, Day 4. So you all know we have a couple of quizzes coming up this week. Tomorrow, I believe, is our review quiz 3. And then either Wednesday or Thursday, I can't remember which day it is, we have a quiz on the mean value theorem. Quiz on the mean value theorem. Our Unit 2 test is about 8 or 9 days off still. And I will be handing back your, maybe 10 days off, I'll be handing back your quiz 5s at the very end. Please get started as quickly as you can on Unit 3, Day 4, warm-up. And let's discuss. Number 1, obviously, a series of derivative skills. So each term kind of represents its own skill, I suppose. And then number 2 is the limit of a product. As long as those two limits exist, the limit of a product is the same as the product of those two evaluated limits. So, be happy to discuss either of those or any of the parts on number 1 there if you want. Anybody have any questions or concerns? What about this, or what if that's, or I don't know. Anything to say? Does have any questions? Let's go okay? That's a good sign. That's a good sign. Okay, well, I'm ready to move on if you are, unless you have a question or a comment. Well, let me ask you a brief question, I guess, then before we move on. With number 1, you guys doing okay with that first term? Okay, the first term is kind of a double chain rule, right? The function inside a function, inside a whole other function. Hopefully that all makes sense. Arcsine is probably the newest of all those that we've seen. The derivative of arcsine of u over a is u prime over square root of a squared minus u squared. I think you can see that represented up there pretty well. Okay. there's nothing else I can add to your education at this moment. Okay, fair enough. So flip backwards if you wouldn't mind. I will do the same. So we're going to go back in time just a little bit. We're going to go back here to what we kind of started with the other day, just real briefly. We looked at this Unit 3, Day 3. And you guys remember this guy's name? Remember how to pronounce his name? L'Hôpital, yes. The hospital for the French speakers in the room, right? So remember we talked a little bit about that limit, and I think I'd mentioned, hey, it's something we looked at with a calculator, and but now we're going to be looking at how to deal with this analytically. The thing I want to focus on with you guys here this morning is the conditions, the proof, and some examples. So you cannot just apply L'Hôpital's rule whenever you feel like it. There are certain very specific conditions under which we can apply it, and we are going to be focusing on two of them. And I'll just draw an arrow to further highlight the highlighting. The two scenarios in which we are going to be using L'Hôpital's rule would be when the limit of the numerator is 0 and the limit of the denominator is 0, or limit of the numerator is infinity and the limit of the denominator is infinity. Okay, those are the only two scenarios in which we will focus on these. Things like this that look indeterminate but really aren't, those are not scenarios where you could use L'Hôpital's rule, so don't. Or you can't just use it because you feel like it. The conditions demand that we either do or don't. Okay? So make sure you carefully check your conditions, and I'll be showing you good ways to do that. So if L'Hôpital's rule conditions are met, then what we can essentially do is take the derivative of the numerator and find the derivative of the denominator, and then reapply the limit. I think I have a note up there that says, yep, this is not the quotient rule. So we're not doing low D high minus high D low over the square of what's below because we're not finding the derivative of the whole expression. We're only finding the derivative of the top, the derivative of the bottom, and then we're trying to reapply the limit. And then one other note here, L'Hôpital's rule can be applied cyclically, like you can try it once, and if you continue to get in one of those indeterminate conditions, you could apply it again. And if you get another set of indeterminate conditions, then you can apply it again. You could do it 2, 3, 4, 5, 200 times. Not that I would have you do that. As many times as needed until you actually get an answer or not in indeterminate form. Okay, so it can be applied multiple times. Let's see here. Can I show you a really basic proof? Okay, so the big boy proof, the big girl proof is beyond the scope of our class. So I'm going to show you I call this the baby proof. Oh, and it's still thinking. Sorry, I'm having some issues apparently. There we go. So this is the baby proof. And hopefully this will suffice for you. So if I have this, the limit as x approaches c of f of x over g of x. Let's say that I have that right there, and I try to apply the limit, and I get, bless you, one of those indeterminate conditions, right? 0 and 0, or infinity and infinity, something like that. And I think, all right, I'm going to apply L'Hôpital's rule. Here's what I could do. I am going to extend my fraction bar a little bit, and I'm going to write f of x minus f of c over g of x minus g of c. So essentially what I'm changing from step 1 to step 2 is I am subtracting something from the numerator, and I am subtracting something from the denominator. The only problem with this is I can't do this mathematically. This is completely wrong. Right? You can't just say 17/30ths. Well, let's just subtract 1 from the top and 2 from the bottom, and it's the same thing. You can't do this unless f of c and g of c are both what? Equal, and equal to what number? Sorry? Not infinity. If they're both 0. If I subtract 0 from the numerator and 0 from the... I haven't really changed the value, have I? I've changed the form, but I've not changed the value, right? So the caveat here is that f of c and g of c are both 0. F of c and g of c are both 0. Okay, so far I've subtracted 0 from the numerator and the denominator. Hopefully you can accept the fact then that I haven't really changed the value at all. Changed the form, but not the value. Next thought. I'm going to take the exact same fraction. Here's my fraction bar. But now what I'm going to do is I'm going to divide the top and bottom by the same thing. So on the top, I'm going to write f of x minus f of c, and I'm going to divide the numerator by x minus c. Now, I'm not allowed to do this either unless I also do what? Sorry?
X minus c has equal 1.
Okay, yes, but there's another, that's true, but there's another way I could balance this out. If I divide the numerator by something,
Also divide the denominator.
yes, if I do the same division to the denominator, I'm still okay. So whatever x minus c is equal to, as long as I divide the top and the bottom by the same thing, I have not violated any math principles. Okay. Then, really the final stretch here on this is I need to recognize, kind of like you did in your warm-up, if I'm doing the limit of a quotient, I can apply that limit to the numerator and the denominator. So my next step would look something like this. Limit as x approaches c of the numerator, bless you, divided by the limit as x approaches c of the denominator. This is really similar to what you just did in your warm-up. The only difference is in your warm-up it was a product that you applied the limit to instead of a fraction. The last step is this, and this might be the hardest step of all in this proof. We need to look at the numerator and see it for what it really is. Same thing with the denominator. So did anybody look at that numerator and say, oh my gosh, it's the derivative of what? Evaluated at? C. So I would say the numerator is f prime of c. Therefore, by the same kind of reasoning, the denominator is g prime of c. Okay? So we started off at the very beginning with this. But somehow we ended up with that equaling the derivative evaluated at c over the other derivative evaluated at c. Like I said, this is the baby proof of this. There's a much more extensive proof based on what's called the extended mean value theorem. And if you ever took like maybe an analysis class in college or something a little more rigorous or something with a little more time, if I was going to teach you that here, I'd have to teach you what the extended mean value theorem is. That would probably be 2 days. And then we'd probably take 1 whole day to use that to prove this. And I just don't have 3 days sitting around to use. That makes sense? We barely have enough time to do what we need to do. You okay with this as a proof? I mean, is it like, said okay? I'm going to hesitate as much as possible from saying, hey, the book said it, or hey, your teacher said it, so you just better believe it. This is an attempt to help you see why. We good? Okay, so while I transition, I want to tell you a very brief story. As you guys know, or maybe some of you know, I have the pleasure in June of being an AP reader. So what I do for about a week is I read thousands of AP tests and grade them, the free response questions. And so it's not just out of the goodness of my heart. I do get paid, but I also learn a lot. And one of the things that I learned a couple years ago is that people mess what we're about to do here, they mess it up all the time. Not because it's difficult, because they mess the communication up. I graded a question that involved L'Hopital's rule several years ago, and you grade the same question all day long. And I'm usually on a team where I get a little more variety, but this one particular time, I graded the same question for 2 days in a row that involved L'Hopital's rule. So it's just like over and over. So you get really good at it after a while, right? It's just like repeatedly, over and over and over and over. So I started to notice a pattern. And the pattern that I noticed is that I went the whole morning, and this one question that involved L'Hopital's rule, nobody got full credit. Nobody got all the points. A lot of people got 0 out of 3, but a lot of people were getting 1 or 2 out of 3. So I started to pay a little more attention to this pattern. I went the whole afternoon, nobody got full credit. So the day 2, still grading the same question. My mind is getting a little numb at this point, but whatever, still paying attention. The whole second day, nobody got full credit. So I went 2 whole days with no one getting full credit. And it wasn't because the question was hard. It wasn't because the answer was awkward. It was because of poor communication. Okay? Basically, carelessness with the equal sign. So I want to show you something about this. We're going to go back and do this one analytically. And I want you to pay really close attention to notation. This is a classic example of where you could get the right final solution, the right final answer, but you will not be getting it correct unless your communication is stellar. So I want to show you, would you like to see a bad example first or a good example first? You want to see good first? Okay, I'll show you good first. So if you've got the limit of a fraction, isn't that equal to the fraction of the 2 limits? So I'll show you. Here'd be an example, a good way to do this. You see that you're doing the limit of a fraction. Maybe off to the side you'd go limit as x approaches 0 of sine of x, and you'd evaluate that. What would you get if you did that? No, we're not doing any derivatives. We're just evaluating the limit.
0.
It's 0. You can just do a direct plug in here and you get 0. And then what if I did the limit as x approaches 0 of the denominator? 0. This is a really good example of notation. I've calculated the limit of the top and the limit of the bottom, and I've gotten a L'Hopital's condition, right? I got a 0 and a 0. So what this means, because I've found this condition to be true, I can now use L'Hopital's rule to help me evaluate this. So again, this is the good example, right? So I come down here, and I would then say, all right, well, I'm going to do the limit as x approaches 0. I'm going to take the derivative of the numerator. So what's the derivative of sine of x? Cosine. Yep, so it'd be limit as x approaches 0 of cosine of x over, what's the derivative of the denominator? 1. And now that I have applied L'Hopital's rule, I can retry the limit, right? Retry it. So as I apply limit as x approaches 0 to cosine of x, what do I get? And the denominator is just 1. So I would say that this equals 1. Therefore, I can go back and say my original limit, bless you, the original limit that I was trying to figure out in the first place also equals 1. So I would say like this right here would be great communication as requested, correct answer, tied it back to the original question. This would be exactly the kind of thing I'd be looking for. Would y'all like to see a bad example now?
Sure.
Okay. So if we started off with the same thing, I'll tell you what, why don't I just work quietly and you can make your observations. Fair enough? So this is a bad example. And I would put this in the category of like a good bad example, because there's a lot right here, isn't there? Compare the two. What's the difference?
Not putting the limit on the numerator and the denominator.
This one is subtle, and that's really it. That's really it. Notice what I said here, and this I think on a lot of folks, I think you're going to figure this out. I think this is lost on a lot of people. Notice what I said in step 1. I said the limit as x approaches 0, sine of x over x equals 0 over 0. And then look what I say just a couple of steps later. The same limit equals... So couldn't somebody then look at my work and draw this conclusion? Do you see why this is really poor communication? Because this is most certainly not the case, right? 1 does not equal 0 divided by 0. But if you look at my work, it kind of seems like it should, shouldn't it? It's one of those bad communication things. Where I really made my mistake is right here. Okay? If you get a L'Hopital's condition, don't tell me that the original limit equals the L'Hopital sort of not really the L'Hopital condition, like a 0 over 0 thing. I would not do that at all. If you find yourself writing this, like 0, fraction bar 0, stop. Erase it and come back over and write something like this. Does that make sense? If you find yourself writing 0, fraction bar 0, immediately erase it. Don't do it. Go back over and write something like you see in purple there. Okay? Here is why we are so picky with communication. Doesn't it seem like L'Hopital's rule is kind of like a magic pill? Oh, just take the derivative of the numerator and derivative of the denominator and voila, magic, you get an answer, right? So we want to be really careful that you understand the conditions that lead up to it so that we know, or at least we have like some hope that you really truly know what's happening kind of behind the scenes instead of just this magic. Oh, just do some derivatives and magic, poof, we get an answer. Okay, how we doing? All right, let's see what's next. And by the way, isn't that answer of 1, isn't that what we got on our calculators? I don't know if you remember, it's like last Friday, but it is what we got. Okay, so I thought this might be a nice one for you guys to try on your own. We're practicing good communication. And I would say, Merrick, I'm not sure what you're doing with your calculator. If you're just investigating, that's fine. But these are typically no calculator questions. So if you would, take a minute. I know I'm kind of pushing you off into the deep end here a little bit. And see if you can have good communication. Use L'Hopital's rule to try number 2. Let me see if I can show you a good example. Maybe you're doing this in your head, right? Because how many of you guys are comfortable just plugging in for a limit, right? I mean, that's what you did originally, way back when, back in pre-calc. So you plug in, and mentally, do you see how you get 0 for the numerator's limit? And then, of course, you got to be able to do a little unit circle stuff here. Sine of 0 is 0, so you can probably see how you'd get 0 down there in the denominator. You're going to need to write that down, and you want to write that down well, communicate, good communication. So here's a way to do that. You'd say limit of the top as x approaches 0 is equal to 0. Limit of denominator as x approaches 0 is also 0. So notice how I've separately shown the limit of the top, the limit of the bottom. The key is separation. I would say this. Are you watching? Not so good. You want to get that fraction bar out of there completely. The truth is, a lot of people think that the AP tests are graded the same way every single year, but that's not the truth. Depending on the year, there are going to be subtle little differences between how things are graded. And, if you have the fraction bar in there, is that good or is that bad? Would this get full credit? Would this not get full credit? So it kind of depends on the question leader. They'll have their opinions. But the one thing that is consistent is that good math is always awarded credit. And this is good math, right? So we might be able to find little loopholes where like 5 years ago they accepted such and such, and 2 years ago they didn't. That's just a question of gray area on what are we going to give partial credit for. Good math is good math and will always get full credit. So I want to teach you to use good math. Okay, so I noticed that some of you guys wrote something like L'Hopital's condition met, something like that. That's awesome. If you want to write that, there's no requirement that you write that, but if you did, just as kind of a note to yourself, no problem. So then when you try to apply L'Hopital's rule, you'd say limit as x approaches 0. It'd be 3x squared minus 12 divided by 3 cosine of 3x as you do your various derivatives, right? The derivative at the top, derivative at the bottom. Now, once we've done this, we're going to reapply the limit. And when I do, in the numerator, don't I get negative 12? And in the bottom, I get 3. So now I can put equals, and of course that equals negative 4. So then I'm always going to bring it back to the beginning and say, therefore, the limit as x approaches 0 of my original expression also equals negative 4. And you can confirm this graphically. You could look at your calculator and notice that indeed this does seem to be approaching 4 from the left and the right, but there's probably going to be a little hole there, right? Why the original limit didn't seem to work. Okay, how we doing? I want to do one more. So if you would, take a look with me, please, at... I'm going to skip a little bit here. give me 1 second. Yes, if you guys would. So this is going to be a little bit of a fast forward. Will you guys flip over to Unit 3, Day 4, Number 4? I wanted to make sure we got one in with infinity and then one other little detail here. While you're flipping over there, one thing I want to mention, there's obviously about 4 or 5 of these practices that we're leaving undone because we're going to move on tomorrow. What I'm going to do is I'm going to make a video of just me working on those other 4 or 5 questions, and I'll post those for you. So if you were like thinking, hey, I know we have a L'Hopital's rule quiz coming up later on, I'd like to practice all those and see those done, I'll just post that video probably in today's folder, and you could always go back and try those and check and hopefully confirm you're doing well. But just look for that video. I'll probably send an email or update about that. So, shifting gears on this one a little bit, when you think about the limit of the top and the limit of the bottom, what do you get in both cases? What's infinity in squared? Isn't that just some larger variety of infinity? I mean, it's not really, but it's infinity, isn't it? And how about e to something gigantic? What do you get? Something gigantic. We'll call it infinity, right? So notation-wise, looks really similar. So you'd say limit as x approaches infinity of x squared. Well, that equals infinity. And limit as x approaches infinity of e to the x. That also equals infinity. This would be a time when those of you that are used to just putting d and e when you see infinity, you're going to want to put infinity here. Okay? So L'Hopital's rule, conditions met. Okay, so we do the same thing. Even though it's infinity and infinity instead of 0 and 0, I'm going to apply the L'Hopital's rule to it the same way. This time I get, what's the derivative of x squared? 2x. And what's the derivative of e to the x? Okay, so as before, once we've applied L'Hopital's rule, we can try the limit again. What's the limit of the top? Limit as x approaches infinity of 2 times x. Isn't it essentially 2 times infinity? And if you double infinity, what do you get? You get infinity. And we already know where the numerator or the denominator is going, right, from before. So this is one of those examples where the L'Hopital conditions are met again. So limit as x approaches infinity of 2x, you said it right, equals that. Limit as x approaches infinity of e to the x, also infinity. So L'Hopital condition met again. So it happened again. No big deal. We don't panic. We don't freak out. We just say, all right, let's do it again. So this time I say the limit as x approaches infinity of, what would my numerator be after I apply L'Hopital's rule? Don't we know at this point that we're done with L'Hopital's rule? How do I know?
Because there's no x in the numerator, it's not going to be infinity.
Isn't the numerator for sure just going to be 2? So there's no way it could be 0. There's no way it could be infinity. So I know that I'm done with L'Hopital's rule. The derivative of the denominator is still e to the x. So, as x gets really huge, 2 over e to the x approaches 0. Okay, let's make a table. I'll erase this. Some of you are looking at me sideways. Okay, so if your input is x and your output is y equals e to the x, let's think about what happens. Remember, x is heading towards infinity, so I'll go, I need to get the right function in there. How about 2 over e to the x? Sorry about that. So if x is 1, then 100, then 10,000, then 1,000,000, would you agree that x is heading towards infinity? 100, 10,000, 1,000,000, right? We're not anywhere near infinity, but we're heading there. Okay, so if x is 1, wouldn't I get 2 over e? And you could use your calculator to evaluate this. This is just slightly less than 1, right? It's like 0.7 or 0.8 or something like that. This would be 2 over e to the 100th. So e to the 100th, that is a really large number, right? So this would be a whole bunch of zeros and then some numbers. Well, this would be, and again, use your calculator if you doubt this. Oops, this would be 2 over e to the 10,000. Again, feel free, use your calculator. I bet you this is going to be almost just 0 as it is. And this, of course, would be 2 over e to the 1,000,000th. Again, encourage you, on your calculator, go 2 over e to the 1,000,000th. I bet you it's painfully close to 0. And we're not even close to infinity with our inputs yet, right? We never will be. But 1,000,000, that's like nothing compared to infinity, right? It's nothing of nothing. And we're already getting super close to 0, correct? You with me? So this goes back, way back to doing some of our limits originally back in August. If the numerator is held constant and the denominator gets gigantic, the overall value is heading towards 0. So I would put equals 0. And therefore, that also equals my original limit, which was, what, x squared over e to the x? For my final. Merrick, you were the chief doubter there. Are you okay with that now? Okay. All right, very good. So, like I said, there's four or five, maybe even 6 examples left undone due to but we've covered the whole thing, right? You just haven't gotten like an extra day of practice, which is what I originally intended. So I'm going to make a video, which would, substitute for that extra day of practice, and I'll post that for you guys. I wanted to hand back your quizzes as well from last time. Derivative Skills 2. So give me just a second to do that. Let's see. Luke, here is yours. Carson, not Cole, however, it is. You are Nate. You are here.
But yes, you do. You learned exactly the same. I don't know. You learn more because you are paying attention.
Maddie is yours. Joseph. There is a Jay. Many of you have the magical, disappearing, radical, and number 1. Some of you had some issues with parentheses, like you had essentially correct answers, but your lack of parentheses made it a wrong answer. Others, yes, just left exponents off when exponents should have been there, and they just disappeared. So I think overall, since things that will be straightforward for you to fix and work on, you do pay close attention to these type of examples. Does everybody have theirs now? They should. Everybody should. Yes, sir. Oh, sorry, Jackson. See, I don't know how to put it in the wrong spot. Hang on. Sorry, Jackson. Yeah, sorry. I filed it away when I should You understand, right?
Yeah.
So just be careful. Be careful that you obviously have all the elements there. Because of the no parentheses come into number.
Luke, you do that too?
I mean, that's what you need to do, right? That's fine. That's totally fine. Okay, I think we're good. You guys can take those with you. Hope you have a good rest of your day. Enjoy BWE. I'll be around for retries in the coming days as you wish. See you guys tomorrow.
You're not-